Hello. Today I'm going to talk about growth functions of periodic tessellations and how to compute them. It's a joint project with crystallographers and chemists, Professor Mariusz Jaskulski and Professor Zbigniew Dauter, and mathematician Dr. Bartosz Naskręcki. Motivations for our research comes from crystallography. A material is crystal if it has essentially sharp and diffraction pattern. This definition encompasses classic periodic structures and quasi-crystals, but in this talk I will discuss only periodic structures. And by n-dimensional periodic structure, I understand structure consisting of motif which is repeated in n direction. As we can read in International Table for Crystallography, crystals are finite real objects in physical space, but they can be idealized by infinite three-dimensional periodic crystal structures. Such idealized crystals are built from identical blocks called unit cells, which are repeated one next to another in three-dimensional space in an infinite number of times and form the lattice. These idealized crystals have translational symmetry. And here we have a small example. We have a unit cell of a diamond and fragment of a diamond's lattice. Important property of a crystal structure are its symmetries. These symmetries form a group named space group or Bilderberg group. Space group is discrete group of isometries of a Euclidean space with compact fundamental domain. And Bilderberg showed that for any dimension n, there always exists finite number of isomorphisms of such groups. In dimension 2, we have 17 of them. They are named wallpaper groups. In dimension 3, there's 230. And as you can see, in higher dimension, these numbers are much bigger. And we don't know number of groups for dimension higher than 5. Crystallography is science of determining arrangement of atoms in crystalline solids. And from the mathematical point of view, you can see it as studying of tessellations of the Euclidean space. Tessellation is countable family of closed sets. Elements of this family we call ties. And if tessellations, then union of this all ties give us whole space. And the ties intersects only on their boundaries. Tessellations considered by us are not necessarily given by polytopes, but they need to be normal. Normal tessellation of Euclidean space is such tessellation that every tile is topological pole. Intersection of any two tiles is connected set, and the ties of tessellations are uniformly bounded, so we don't have arbitrary small or big ties. As I said before, we consider only periodic structures, so we'll focus only on periodic tessellations. We can generate whole periodic tessellations just by copying and translating a fragment of it. In case of this example, the tessellation is generated by translations and region marked red. Our goal is to build numerical variants of tessellations, which can describe tessellations in various ways, especially topological and rigid. And to achieve it, we defined two types of growth functions. We did tessellation as a CW complex. We consider tessellation of the whole space as inductive limit of growing sequence of finite tessellations. And we are interested what are numbers of cells of different dimensions in this finite tessellations. So we are constructing approximations of tessellation by finite tessellations, and we ask about number of cells in these approximations. Here we have a two-dimensional example. So we have zero-dimensional cells, which are vertices, one-dimensional cells, which are edges, and two-dimensional cells, which are faces. On the picture, they marked respectively red, orange, and blue. So growth functions counts number of cells of given dimension in finite fragments of tessellation. And we start from logical growth functions. Here we have a two-dimensional example, and that's why we have three growth functions for this one tessellation. They took two parameters. First one, omega, is simply connected CW complex that we can use to generate whole tessellation by translations. And second parameter n describes number of translations that we can make with our omega by generating finite tessellation. For simplicity, I will in this talk only talk about n being single number, but of course we can think about n as a vector, and in that case we would have a different growth in direction, but I will not talk about it today anymore. The darkest fragment here corresponds to n equal to 1. If we add to this darkest part also this little brighter, we will get a finite tessellation that corresponds to n equal to 2. And this whole image corresponds to n equal to 3. We consider periodic tessellations, and that's why our growth functions are polynomials. So let omega be again simply connected CW complex that generates whole our tessellation. And if you are in two-dimensional space, then we can divide its boundaries into 2 or 3 pairs of transversional equivalent fragments. For example, alpha plus alpha minus, beta plus beta minus. So in other words, every periodic tessellation of two-dimensional space can be realized with generalized quadrangle, case A, or hexagon, case B. And we can use this division of a boundary to give formulas for topological growth functions. In these formulas, this absolute value of omega 0, omega 1, omega 2 means a number of 0, 1, and 2 dimensional cells inside omega. Absolute value alpha plus and beta plus means number of one-dimensional cells, in other words, edges. In these fragments, alpha boundary alpha plus and beta plus. Topological growth functions are insensitive to the topological deformations, and they can be used, for example, to distinguish topological type of tessellations once given partial or corrupted data. Before I will move on to a small experiment that we made, I'll introduce two tessellations. First one is 4, 4, 4, 4. It consists of only of squares, and its name comes from the fact that this basic tile, which is square, has 4 vertices of degree 4. The next tessellation, 884, is constructed using triangles. And again, it's named 884 because this basic type has two vertices of degree 8 and one vertex of degree 4. So for experiment, we generated a fragment of tessellation 884. In next step, with probability P, we were removing central vertices and coincident edges from our tessellations. And after corrupting our tessellation, we started computing group polynomials, but starting in different fragments of tessellations. So we were looking on fragments of tessellation and tried to and then we were calculating group polynomials. After that, we averaged coefficients of these polynomials, round up by coefficients to integers. And we tried to classify tessellations using this averaged and round up polynomials. So if we get polynomials characteristic for 884, we then classify our corrupted tessellation as 884. The same for tessellation 444. But of course, in many cases, we also get polynomials that didn't fit to any of these cases. It wasn't polynomials for 884 or 4444. And as you can see, here are the results for experiments. We repeated it 1,000 times for any set of parameters. As you can see, if probability of removing central vertices were relatively small, then our tessellations were mostly classified as 884. Number of tessellations classified as 884 increased when we increased number of samples. When you take parameter p equal to half, so this it was a situation when to the same degree our tessellation was 884 like 4444. When for a small number of samples, generally we almost never was getting of these polynomials, but you can see it changed when we again increased number of our samples. Now I move on to next type of group functions, crystallographic group functions, which measure growth of tessellation against the propagation of a unit cell. So we are taking in general case of the two-dimensional space parallelogram frame with fixed anchor point, and we just count number of cells which are inside this frame. Again, we study periodic tessellations, and our frames are compatible with translational symmetries of the tessellations, and that's why we again get polynomials for n big enough. Because for small n, it's not always polynomial. Okay, and here example how we can calculate such crystallographic group functions. So in case of crystallographic group functions that counts number of vertices, it's very straightforward. We get similar formula like for topological group functions, and it works also for high dimensions. In case when we have sets of high dimensions like faces, edges, and even more dimensional sets, then we can, for example, first compute impact of every translational unique cell dimension k, and then some results. Here's a small example. We have frames with anchor point x, and we have edge e. And as you can see, we need to extend by one our frame in one direction to have full edge inside the frame, and that's why impact of this edge on a growth function is n-1 multiplied by n. Of course, there are in general different special cases, but I showed this. Of course, there are also different methods for finding these polynomials, but I give it as an example because it nicely extends when we want to compute crystallographic growth functions for all possible placement of a frame. Because as you can see on the slide, these functions are sensitive to the selection of anchor point of the frame. If we place our frame in different place, then we can get different growth functions. But it's not necessary, because for every tessellations, there always exists finite number of these crystallographic growth functions, and we can divide our space into the regions in which growth functions are the same. We can mark them by different colors, and after such procedure, we get diagrams like I presented here. We have here. We name this. We call this diagrams orthogonal diagrams. We have diagrams for two tessellations, for one in every row. As you can see on the picture, there are two-dimensional and one and zero-dimensional regions within which growth functions are constant relatively to the anchor point. Here's an example example for two-dimensional space, but of course you can think about complete diagrams also in high-dimensional space, but visualization would be more problematic. Okay, and now I will explain how they can be computed. This method is implemented in our Julia package available on GitHub. So first we convert our data to fractional coordinates. The same vectors that defines our frame will define also our coordinate systems. It is periodic tessellation, so we only need to look inside a unit cell to create our diagram. So in next step, we draw lines, these dashed lines going through vertices and parallel to the frame, to the sides of the frame. These lines give us skeleton of the diagram. At this step, we can see all regions with possibly different growth functions. Growth functions of different regions are interrelated. It especially applies to the growth functions of neighboring areas. So to save the time in the next steps, we now record which edges start and end every dashed line, because only these edges are important when we go from one region to another across these lines. I talked here about edges, but at least in case of selection given by polytopes, procedure for higher dimensional cells, 2 and more, are very similar for edges. They are like for edges. Okay, so we start from calculating crystallographic group functions for one vertex. And in the next steps, we iteratively compute group functions in all other regions based on already found group functions and information that we recorded earlier about which cells starts and ends at these dashed lines. And this way we get our full diagram. All this previously this full orbit diagram presented before, not in an example, were generated by our Serbach package. We also have a Julia package which concentrates more on efficient finding these orbit diagrams and on group functions. They are available on GitHub. So in future, we would like to find what is the relation between these crystallographic group functions, orbit diagrams, and symmetric group of original tessellation. It would be great if you could find a nice way to go from orbit diagrams to the symmetry, to the space group. We are planning to use machine learning tools. We are going to train a model on our orbit diagrams to recognize space group original tessellations, and we are going to interpret training results, hoping for some clue based on which we could create hypothesis and after that create a formal proof. I would like to know what part of these orbit diagrams are really important to determine symmetry of original tessellation. And that's all. Thank you for your attention.